All right, this section deals with acylation of amines, and it's a pretty neat section. It has some really interesting chemistry in it. So, first of all, you have to remember from back in chapter 20, the carboxylic acids in their derivatives chapter, we would have looked at acylation of an amine. And of course, here you need 2 moles for every 1 mole of your acid chloride because you have to neutralize the HCl that's formed in the reaction. But anyhow, the bottom line is you take your amine, okay, and you convert it into an amide, okay. And so it turns out that the acylated amine can actually be used as a protecting group, okay. So take home message, acylated amine can be used as a protecting group. So let's see how we would use that as a protecting group. Now, before we can use acylation or an acyl group as a protecting group, we have to go back and revisit the bromination of aniline, okay? Now, you remember that if you have an amino group on your aromatic ring, right, that's going to donate a lot of electron density to the ring via resonance, right? You have a lone pair here, and you can start drawing resonance structures like this. So very electron donating, and therefore when you have this amino group on your ring, it's very highly activated, okay? So the amino group is a very powerful activating group. So if you take aniline and you just treat it with bromine, okay, no iron catalyst required, it just brominates everywhere. It goes in both ortho positions and in the para positions. Now, what if you just wanted to monobrominate? Okay, what if you just wanted to add 1 bromine to your aniline? Well, how would you do that? The way you could add just 1 bromine in the para position to your aniline is shown here, okay? Now remember, when you have aniline, right, it's too activated to just treat it with bromine. However, if we acylate it, and you see that shown here in the first step, once we add the acyl group, remember, the carbonyl is electron withdrawing, and you could even draw a resonance structure here where you show the electron withdrawing effect of that carbonyl. So what the carbonyl does, or the acyl group, is that it mitigates the reactivity of the aniline. So now it's not aniline, it's acylated aniline. So it's going to be less reactive. And so when you treat that with bromine, it adds 1 bromine in the para position, right? Because it's less sterically hindered than the 2 ortho positions. And then you can hydrolyze this bond one of 2 ways. You can do it in strong base or strong acid, which is kind of the disadvantage of this synthesis, is that it does require harsh conditions. So when we're talking about just using acid or base, it is a bit harsh. But again, if you want to make parabromoaniline, this compound here, it's the best way to do it. Now, something else you might remember from back in chapter 18 is that aromatic amines do not undergo Friedel-Crafts reactions. You can't do Friedel-Crafts alkylation or acylation with an aromatic amine, an aniline derivative. And the reason why is that the aniline acts as a Lewis, this is a Lewis base, an electron donor, and the aluminum trichloride, of course, is a Lewis acid. And those two react together. You can see the base donating electrons to the acid, and then you make this Lewis acid base complex, and look at this. We got a positive charge plunked right here on the nitrogen, and now the ring is deactivated. I mean, highly deactivated. And you remember that Friedel-Crafts chemistry doesn't occur when you have a highly deactivated ring. And thus, in order to achieve Friedel-Crafts alkylation, what we do to prevent the aniline from acting like a Lewis base is we acylate it first, right? Once we add that acyl group, right, you go from the amine, which is nucleophilic, but the lone pair on the nitrogen here in this amide, this is not nucleophilic. So what I'm putting here in the blue circle, not a nucleophile. And so it's not going to react with the Lewis acid, and so we can do our Friedel-Crafts chemistry here, no problem. And then again, we knock off the acyl group, we hydrolyze it either with strong acid or strong base. Okay, kind of a long question here, but it gives us some information. It says when aniline is treated with a mixture of nitric acid and sulfuric acid. So if we take aniline, so we should memorize the structure of aniline, and we treat it with a mixture of sulfuric acid and nitric acid, right? Those are the conditions for nitration, and the nitrogen is an orthopara director. So what you might expect what you might expect is that you would make para-nitroaniline. Well, let's read on. It says the expected nitration product, para-nitroaniline, this compound is obtained in a poor yield. Instead, the major product is meta-nitroaniline. Okay, so apparently the amino group is protonated under these acidic conditions, and the resulting ammonium group is a meta-director rather than an ortho-para-director. So what it's telling us is this. Since you're in very strongly acidic conditions, you actually don't have aniline. What you have is this, the protonated aniline, and this is a meta-director. And so instead of the nitro group going in the para position, it actually goes into the meta position like this. So what the question is asking us to do is it says, can you outline a method for converting aniline? So if we wanted to take aniline and we want to convert it into para-nitroaniline, well, how would we do that? Okay, so we want to convert it into para-nitroaniline. Well, the answer is going to be acylation, right? Because if we acylate the amine, then it's not going to be protonated under acidic conditions when we try to do our nitration. So let me outline this for you, okay? So we're going to start out with our aniline, and the first thing we're going to do is we're going to acylate it. So we're going to treat it with our acetyl chloride. So we install our acyl group, and now it's still an ortho-para-director, but now it's not nearly as reactive, and it's not going to get protonated under the strongly acidic conditions of sulfuric acid and nitric acid. So we're going to, oops, there we go. I don't know why I put nitrous acid. Anyhow, must be thinking ahead in the chapter. All right, anyhow. So let's see here. So now we have our acyl group like this. Now we have our nitro group, oops, our nitro group installed in the correct position. Remember, this is still an ortho-para-director. And so now to hydrolyze, we could use strong acid or strong base. I'm just going to put, I'll just put sodium hydroxide. You could put H3O plus. Either one is fine. And so that's going to give us our para-nitroaniline. You know, this question is really great because it illustrates a lot of what organic chemists do, which is try to dream up new ways to make molecules that, you know, are difficult to make, you know, and this is a tricky synthesis. So you have to understand that the acylation is going to mitigate the reactivity of that amino group, and it's going to allow you to put that nitro group in the para position exactly where you want it. Question 22.21, it looks pretty simple. It says starting with nitrobenzene and any other reagents. So if we're starting it with nitrobenzene, could we find a way to make parachloroaniline? Okay, so we want to make this compound, parachloroaniline. Okay, and you might think, okay, well the nitro group is a meta-director. Once I reduce it down to the aniline, right, which is pretty straightforward, it's going to be an ortho-para-director, and then all I have to do is just treat it with chlorine. But the problem is, if you were to do that, the ring is so highly activated that what you would actually end up with is chlorines in both of the ortho positions and the para position, and probably a mixture, okay? So this is not going to work. So we need to find a workaround here, okay? And so what we're going to do is we're actually going to make the aniline first, but then we're going to acylate it, which will mitigate the reactivity. And then we're going to knock off the acyl group after we do our chlorination. So what's that going to look like? Well, maybe I'll just erase some of this, and that way I'll have a little more room to work with. So why don't we start our synthesis going down like this? So we want to make this compound, parachloroaniline. So the first thing we're going to do is we're going to reduce the nitro group down to the amine, and for that I can just use zinc and hydrochloric acid. So we'll put here zinc and HCl, or you could use iron and HCl. Either way is fine, whichever reducing agent you want to use. All right, now we're going to install our acyl group. So let's put in our acyl group. So for that we need acetyl chloride. That's going to install our acetyl group, which is going to mitigate the reactivity. And so when we go and treat this molecule that I'm drawing right now, once we treat that with chlorine, okay, so if we treat this guy with some Cl2, it's going to put that chlorine exactly where we want it in the para position. All right, like that. And then we can hydrolyze, right? We can knock off the acyl group using strong base or strong acid. I usually like to write strong base because presumably if you use strong acid, it's actually going to protonate the amine and then you'd have to treat it with base again anyway. So I usually just like to write just sodium hydroxide is the way I usually do it, just to kind of cover my bases or make sure I got it done correctly. All right, there you go. So using an acetyl group as a protecting group. All right, make sure you understand how to use that acetyl group as a protecting group on your aniline.